All right, welcome to the next lesson, Math 1040 Intro Stats, the central limit theorem. This one is actually super important. We've been learning all about probability and sort of building towards this. And this one can be a little bit hard to understand, unfortunately, but it's the most important thing. The real payoff of the normal distribution is what we're about to talk about. So let's get into it. Big picture time. In statistics, what we're generally trying to do is identify a population, get a representative sample, get data from the sample, summarize that data, and say something about the population. And so we're going to take a random sample and get a sample mean, for example, of a numeric variable, which we're going to call x bar. And x bars are a relatively reasonable estimate of the corresponding population mean, mu, if the sample is good. The problem with this, though, is x is actually a random variable. It's just an estimate. It's not the actual value. So if we don't know if it's the real value, what's the point? Well, in certain cases, we know what the probability distribution is going to look like, and we can attach numerically a way called the standard error, which we'll see in a minute, to account for the variability that would have come from the randomness of the process. So let's see this little applet here, which I've opened up over here. So what we're looking at up on top is some kind of a distribution of data for a population. We'll start with normal and try some others. And these are just numbers. There's no real context here. If it helps to think about it, we can invent a scenario for it. So we could say this is the age of a bunch of kids, and they happen to be mostly around 10 years old or 8 to 12 years old. So the mean of this data is 10 and the standard deviation is 2. And what we're going to do is take a random sample out of this population of size 30. So if this is truly random, a lot of the values will be close to 10, 8 to 12 maybe. There won't be very many values in the 4 to 6 or 14 to 16. So let's hit the button. So this is my random sample. I got quite a few values close to 10. I actually got a really strange value that was very far away. This is just randomness. And so my sample of 30 is on this dot plot, and we could take the mean of these sample of 30, and it's 9.8 roughly, which is not the population mean, but it's actually fairly close, especially considering we got this outlier. Let's try it again. Let's do another one. So I got a sample again of 30, and I got a couple values here, and a lot of values within one standard deviation of the mean, essentially. And that time my sample mean is a little above the real mean. And I'm graphing down here the x bars. So I've done this twice. I have 2 x bars. And so this is the actual sample, and this is the x bar. So x bar is a random variable too. Let's try it one more time. There's my new sample. And my sample mean was really close to the real mean that time. And yeah, so that was really good. Here's what we're going to do now, though. Instead of going one by one, we can do one by one a few times. I'll click this a whole bunch of times. So I don't know how many times I just did that, like 10 or 20. So I'm graphing down, and this below, I'm not graphing. This website is graphing each x bar on the dot plot now. And this is the mean of the means. So all of these x bars that I've gotten that I've graphed down here, and we take the mean of those, it's 10. And there's a standard deviation of all the x bars too. But now what we're going to do is just go huge and do this like 10,000 times. Let's do 1,000. So what did we just do? We took a sample of 30, found the mean, put it on the dot plot. We did that again and again and again. And we did a sample of 30 1,000 different times. So this is the 1,020-ish X bars that I got. And this is the mean of all the means. So what happens here is this is actually the expected value of X bar given any sample. The mean of the means will be the real mean. We're only going to do one study, but this is important. This is the number that's more important, though. This is the standard deviation of my 1,020 X bars, which it tells me about the accuracy of any given X bar. Even if I don't know the real mean is 10, if I know what this is, I can get an idea of how close I was to the real value. And that's the key idea here. And we do know what this is going to be, and I'll show you in a minute. So let's try another one, though. Let's try a skewed distribution. So this is a beautiful right skewed distribution. The mean is 3, that's right here. The standard deviation is 2.5, and there's a few values that are very far away from the mean. And we can do a sample. And we would expect most of our individual draws from the sample to be close to 0 to 3-ish. There they are. And we actually got a couple of these rare ones in our sample of 30. But nevertheless, our sample mean is still pretty close to the real mean. Let's try it again. Let's just go one by one for a minute here. This is my new sample. My sample mean is a little bit above the real mean. Right here. And let's just do a handful of times. Let's simplify, let's reset and go to 0. Do skewed. And I just did one, we'll do 999 more. So I've now done 1,000 samples of size 30 from this, and I'm summarizing the 1,000 X bars. Now let's click this. So the distribution of the X bar is approximately normal here, even though this distribution is really skewed. And this is a key idea, actually. If we know the distribution of X bar is normal and we can calculate this standard deviation, then there's really cool things we can do and we'll learn about in future lessons. All right, so let's go back to the notes. This is the central limit theorem, is what we've just been seeing. And there's some rules here that you're going to need to know. So if the sample size is large enough, which is a strange way of saying, if we know the population itself is normal, then the sample is always large enough. If we don't know anything about the population data, or if we do, but it's skewed or whatever, then a sample of 30 or bigger is enough. So if either one of these things happens, and we have a random sample, that's super important because a random sample is the only way we can get a sample that actually represents the population. Then the sampling distribution of sample means will be approximately normal. That's what we just saw here. This sampling distribution of X bar is normal. Furthermore, the mean of all the X bars will be the real mean. So let me say that again. The mean of all of possible sample means is the population mean. So if we repeated this forever, this real mean was 3 of the actual data, and my mean of means down here is converging to the real data. So if I don't know if this is going to blow up. It's probably going to blow it up. I think I just blew up their website. If we did this a lot, then the mean of all the X bars would be the real mean. And that's important because we're talking about expected value here. Yeah, I just killed it. Sorry, Staplet. We'll try again. skewed. So we'll go a little bit smaller. Instead of 9, we'll do 10,000. Hopefully they can do that. Oh, cool, that was fast. So the mean of the 10,000 sample means is basically the real mean, population mean. That's cool, but this next one is the more important thing. The standard deviation of all the x bars is the real standard deviation divided by the square root of this sample size. And we call that the standard error. So let's actually do a quick calculation. All right, hopefully this works. All right, hopefully you can see the calculator and the screen at the same time, website. So the calculation is the real standard deviation divided by the square root of the sample size. So if I take this real standard deviation of this population data divided by the square root of, I'm doing a sample of 30, I get 0.447. And this down here is the actual standard deviation of the 10,000 simulations of this process. So what is the point of this? This formula calculates what would happen if we were able to do basically 10,000 studies. But that's neat because we're not going to do 10,000 studies. We're going to do one study. But because this is true, we can get an idea of how close our x bar, our one x bar that we get, how close it is to the real one. Because remember, the standard deviation measures spread. So let's just do one more sample. Or we can just take this one that just happened, the last one. If we take this x bar and do a plus minus of the standard error, we should be pretty close to the real mean. And we'll actually end up doing two standard errors worth, but that's later. So just to sum that up again, this value tells me how close my sample mean is to the real mean, give or take. Okay, let's move on. So this is called the standard error, and we'll be using this formula. Okay, next up is sample proportions. And so the central limit theorem also applies to sample proportions. And the same thing is super important. When we take a random sample from a population and we get a p-hat, that p-hat is a random variable, and it's an estimate with some probability distribution of the real proportion that we're trying to measure. So let's back over here. And this one's actually super weird, but really cool. So here's a categorical variable. And you could think about this one like flipping a coin. There's a 0.5 probability of success, and we can call this heads and tails. So 0.5 for heads, 0.5 for tails. And you can manipulate this, which we might do later. So we'll take a sample of 30 from this distribution, like 30 flips of a coin. Okay, so it looks like we got 60% heads and 40% tails, essentially, in that sample. Let's do it again. We'll go one by one for a minute. That time we got a really strange one, actually. 76% heads. Let's go a couple more. I'm just going to start clicking. So I'm doing samples of 30 over and over. Each one of these represents the sample proportion for a random sample of 30 draws, or 30 coin flips. And then let's just go big and do 1,000. So what happened here? That looks normal. In fact, let's click that. We superimpose this normal curve on top of our actual data, then that looks great. So the distribution of the p-hat under certain conditions, which we'll talk about in a second, is normal, or approximately normal. And more importantly, or maybe not more, as important, it comes with also a standard error that we can calculate, and we can know what this number is going to be. So let's talk about that. For a categorical variable or a proportion, the sample size must be large enough, which is a different calculation here. N times P must be greater than or equal to 10, and N times Q must be greater than or equal to 10. And the sample needs to be random. You should just always know the sample needs to be random for all of the stuff we're about for the rest of the semester. The sampling distributions will be approximately normal. That's the takeaway, which we just saw here. And the mean of the sample proportions will be the real proportion. So yeah, I got some weird sample proportions while we were going, but actually the mean of all 10,000 of the p-hats is the real 0.5 that I started with, the real proportion of success. And the standard deviation is the square root of p times q over n. So let's actually calculate that. P is the probability of success, Q is the probability of failure, which is 1 minus P, and there's my sample size. So the theoretical standard error is 0.091, and my observed standard error is 0.091. It's pretty cool. And again, why this matters is we're actually just going to do one study, but we can estimate this so that we can know about how close we are to the truth. That's what this is telling us. Give or take, how close are we to the truth? Okay. So let's back up. And there's one more thing that we need to talk about. I know this video is getting kind of long, but stick with it. We'll go back to the means. The population data is normal or the sample size is greater than 30. Let's show what happens when that's not true. So let's go back to the skewed distribution, and we're going to take a small sample, like 5. If I take a sample of 5, now that's my one sample of 5. It's not very accurate. And then let's just do 1,000 of these. And this is the distribution of my 1,001 X bars. And it actually looks fairly normal, but there is a bit of a right skew here. This rule of thumb, it's just a rule of thumb, is very, very conservative. So even my sample of 5 was pretty close, but basically we would say it doesn't meet the criteria. And so it wouldn't be good enough. Let's do normal. So if the parent distribution is normal and we have a small sample size, let's just repeat that 1,000 times. The sample mean distribution is normal. So if the data is normal itself, the sample size doesn't matter. If the data distribution is something else, we can even try uniform, which looks like that, then that's actually pretty good. But like I said, the rule of thumb is very conservative. Let's go back to the skewed one. Let's do samples of size 3. And we'll do 1,000 of them. So that's pretty ugly. Then we would bail out. So what this really means is this is a known thing. So when you're designing a study to begin with, if you know the population data is approximately normal, then you can get away with any sample size. But if you don't, then you just shoot for at least 30 in your sample. Let's look at the p-hat one now. So this rule of thumb. Let's try one where the proportion of success is 80%. We'll go back to the 30. So this is a scenario, maybe you could think about this like an NBA player's free throw proportion of success. They make 80% of their free throws. But in a random sample of 30 of their free throws, they actually made 93% in that one. And we'll do 1,000 of those, a couple thousand, and this is approximately normal, even though it's not 0.5, because 0.8 times 30 is 24, and 0.8 times let's see, what we're doing is validating this math right here. N times P, that's P, that's N. So, sorry. N times P, oops, P's 0.8. That's more than 10. N times Q, that's not more than 10 actually. So this would be a case where we couldn't say that the central limit would work, even though it kind of looks pretty good. And these rules of thumb are very conservative against saying something that's not true. So let's go with, to make it better, what we would need to do is basically increase the sample size to say 50. That's 10, and 50 times 0.8 is 40. So a sample of 50 would be more appropriate here. And we get a nice normal curve. Let's show one that's definitely not right though. So suppose we do 0.9 and I do a small sample. This is what we're trying to avoid. So with this proportion and this small sample, our distribution of the p-hats is definitely not normal, right? This is what we got, these vertical lines. This one's too tall, and then there's just nothing over here. So 0.9 times 10 is just 9. Which doesn't meet the criteria, and then 0.1 times 10 is way too low. So here's a rule of thumb that says if this is true and this is true, we're like pretty much guaranteed that the distribution will be normal. If either one of these is not true, then we're going to say the sample's not big enough to be safe. All right, we're going to wrap up the video there and focus on basically how to do the homework problems in the next bit.